SOKENDAI in Tsukuba, and he's going to talk to us about complex Langevin analysis of two-dimensional U1 gauge theory with a theta term.
Thank you for introduction, and thank you for giving me this opportunity to give a talk. So I will start my talk. So I will talk about my recent research of two-dimensional U1 gauge theory with a theta term by using complex Langevin method. So this is a collaboration with these people in SOKENDAI and KEK in Japan. So I will go. So I'll first show an introduction. So I'm focusing on gauge theory with a theta term. The theta term reflects topological property of the gauge theory, and its effect is not purely non-perturbative. So theta term is defined like this. This is a four-dimensional case. So this theta is a real parameter, and Q is a so-called topological charge given by this kind of integral. So theta term is actually interesting in the well-known strong CP problem of QCD. Strong CP problem is, in fact, we can include this theta term in the actual QCD of standard model. However, the experimental bound of this parameter theta is extremely small, like this, 10 to the minus 10. So this is a kind of naturalness problem. We don't know why this parameter is so small. So only for the standard model, we cannot explain why it's so small. So the well-known solution of this strong CP problem is a so-called Pechquin mechanism, which introduces axiom. This is one of the interesting topic related to theta. So another interesting topic is recently the Topological anomaly matching is studied by some people, and this Topological anomaly matching condition gives interesting prediction about the phase structure of four-dimensional SU2 gauge theory around theta equal pi. Actually, this point, theta equal pi is a phase transition occur. So there's many interesting physics around here. So in fact, this is related to our future work. So I will explain briefly later. So let's go to the next. So as I said, the theta term is actually give a non-perturbative effect. So the numerical simulation of lattice gauge theory is useful to investigate this theory. However, Monte Carlo simulation of the lattice gauge theory with the theta term is very difficult because theta term is purely imaginary. It means total action is complex. So it is impossible to interpret Boltzmann weight, this factor, as a probability in the Monte Carlo simulation. So this is known as a sign problem. It's a very well-known problem in this field. This sign problem arises in various cases, not only the theta term, but also finite density QCD and higher Feynman system, and also IKKT matrix model. This is related to my previous work, motivated by superstring theory. So very many interesting models is actually very difficult to investigate because of sign problem. But actually, there are some approaches to this kind of complex action system. So I will briefly introduce some of them. The very straightforward method is so-called reweighting. So this method treats a phase factor of Boltzmann weight as an observable. So only absolute value of this factor interpreted as a probability. So instead, the phase factor is included in the observable. However, this method does not work if the phase oscillates rapidly. So I will show the example of this analysis by reweighting method. This is a bit old work. This work focuses on 2D U1 gauge theory with theta term. This is same model with as our work. So this graph is a theta dependence of free energy, and solid line is an analytical solution. And these points are result of simulation. You can see that from around here, the result of simulation is deviate from analytical result, but the error bar is a bit smaller than it's smaller. So this is a very dangerous situation to investigate this model. So actually we can use reweighting method, but there is a limit to apply this method. Actually, if we go to large, if we increase the system size, this problem is become more serious. So to avoid this phase oscillation, there is a technique, so-called Lifshitz symbol method. So this technique is it reduces the phase oscillation by deforming the integral path or the path integral from real axis to complex plane. So this is clearly the improvement of reweighting, but it works well. However, the difficulty of this method is high calculation cost. So there is another method. That is a complex random method. So this method, the computational cost of this method is lower than Lifshitz symbol. However, there is a condition which must to be satisfied to justify the result. And recently, there is another technique, so-called tensor renormalization group. It is easy to increase the system size in this method. However, it is difficult to go to higher dimension in this method. So in this talk, I will hope, and in my research, I use complex tangent method. So, okay, I will explain the complex tangent method. So, complex tangent method is based on usual real Langevin method. So, the system is developed by we consider the fictitious time evolution of dynamical variables, which satisfy Langevin equation. However, in complex tangent method, the real variable is generalized to complex variable, like this. So first we consider real Langevin equation with variable x, but this variable is generalized to complex number z, like this. So this is a complex Langevin equation. So the dynamics of the fixed time evolution of dynamical variable is determined by this derivative of action, which is called drift term, and also Gaussian noise. So this method does not use probability, so there is no sign problem. However, as I said, there is a condition required to be satisfied. That is this statement. the distribution of the direct term, this term, falls off exponentially or faster. If I explain let me explain graphically. So if we plot the histogram of drift term in log-log plot like this, we get some distribution. So this statement claims that if the distribution falls off faster than exponentially, like this blue line, the given result is correct. However, if the distribution falls off like power law, like this red line, the given result is not justified. So if we use complex tangent method, we have to take care. We have to check this condition to justify the result. So this is the end of introduction. So if you have a question, please ask me. So this is the contents of today's talk. I finished the introduction. Next, I will explain the naive implementation of complex tangent method to two-dimensional U1 gate theory. Next, actually there is a problem in this naive implementation. So I will explain how it is improved, and I will show summary. Okay, so I will briefly review the two-dimensional U1 gate theory. So theta term. This model can be solved analytically, so it is good for test of the method. So we can choose this model. So the total action is given like this. This is a usual kinetic term, and this is theta term. So in 2 dimensions, theta term is given like this. So this topological charge is integer on the compact manifold. So we regularize this theory on the lattice. So we introduce usual link variables and bracket. Kinetic term is described by a standard Wilson action. So here now manifold is 2 dimensions. So the bracket is only the 1-2 direction, and it's inverse only this. So this parameter beta is related to the original coupling Z, and A is a lattice spacing. And we also need to regularize topological charge onto the lattice. Actually, there are two types of definition. First definition is like this, which gives an integer, exactly integer for a finite lattice spacing. So it's given by log of bracket. So it pick up a phase of bracket. But here, this logarithmic function is a complex logarithmic function. So it has branch cut. So the property of this definition is it's given exactly integer value, and it changes discontinuously if the phase of bracket go across the branch cut. And the reason why it's given integer is understand by like this. So this factor summation of log is related to the log of product of brackets. But on the 2-dimensional torus, this factor is always unity. So this term vanish. So only 2 pi I times some integer remain. So this factor gives the integer. Another definition, the other definition is given by this, which approaches an integer only in the continuum limit. So on the finite lattice, this definition does not give an integer value. So we consider 2 types of definition in this one. So next, let me explain how to apply the complex tangent method to this model. So we consider discretized complex tangent equation for the link variable. So for the link variable, the complex Langevin equation is given by this. So epsilon is a small number, which corresponds to the time step size. So the evolution is determined by this factor. This term corresponds to the drift term. This d and mu s correspond to the group derivative of the action. And this term corresponds to the Gaussian noise. So in complex Langevin method, the dynamical variable is generalized to the complex. So in this case, the link variable is no longer unitary. It's generalized to complex without zero. So the gauge group is extended. And the drifter and the observable have to respect homomorphicity. This is an important point. So this is the reason why I use U inverse instead of U dagger. So this U inverse respect homomorphicity. So I will use U inverse in the definition of drift term and observable. And actually, in complex action simulation, we use some technique. One of the technique is so-called gauge cooling, which can stabilize the simulation. So the gauge cooling is a technique to use gauge transformation to keep the link variable close to unitary. As I said, now gauge group is extended. So there is a extra degree of freedom in each link variable. So we can consider the gauge transformation for this extended group, for extended direction. And we can suppress, we can reduce the non-unitarity as much as possible. But important point is this method does not affect the gauge invariant observable. So we can trust the result of simulation. So as I said, there is two types of definition of topological charge. So I will explain the difference of two types of definition on a torus. So as I said, logarithmic definition is given integer value, even for finite lattice spacing. And this sign-like definition is it's not integer, but approaches an integer in the constant limit. So in this sense, this logarithmic definition looks better. However, there is a problem. The problem is a drift term. So since this logarithmic definition gives a discrete integer value, so the actually derivative of this Q log is ill-defined. So we cannot apply complex Langevin method if we use Q log. On the other hand, Q sign, this definition gives a well-defined drift term. So in this study we use first we use sign definition in theta term. So I will show the result of naive implementation. So actually the naive implementation is failed because there is two reasons. So it's depend on the parameter region of beta. If we choose a small beta, that corresponds to coarse lattice, the wrong convergence of complex Langevin method happen. Wrong convergence means the condition for the correct convergence is not satisfied. It corresponds to this figure, the purple line. This is a distribution of the drift term in log-log plot. So you can see that it is a power law behavior. So the distribution have to follow faster than exponentially. So this case, that condition is not satisfied. On the other hand, if we choose large beta, that correspond to fine lattice. So-called freezing of topological charge happens. Freezing means the configuration is confined in a single topological sector. It means if we look the history of topological charge during the simulation, it almost constant value, like this green line. So this green line corresponds to fine lattice. So the topological charge is always stay around 0. So the topological sector is confined. So these two problems are actually trade-off problem. So if we choose small beta, the wrong convergence happen, but freezing doesn't occur. But if we choose large beta, wrong convergence does not occur, but freezing of topological charge occur. So how to judge that freezing is? Actually, we know the analytical solution of this model, so we can plot the expected distribution of topological charge like this line. But this is a result of simulation. You can see that the result of simulation only localized around 0. There is no configuration in the topological sector ±1 and ±2. So okay, we show the given observable of these results. So I focus on I choose the average bracket as observable, defined like this. It's like action density. So we plot the simulation data and also analytic solution by dashed line. For small beta, you can see the simulation data cannot reproduce this almost quadratic behavior of average bracket. The simulation result is just looks like linear. Of course, only at theta equals 0, there is no sign problem a priori. So there is no problem. So only theta equals 0, the observable is okay. On the other hand, for large beta, we can also plot the simulation data and the analytic solution. In this case, freezing of topological charge also occur at theta equals 0. So freezing is always happen independent of theta. So for every parameter region, the observable is different from analytic solution. So actually, for two-dimensional on the two-dimensional torus, we cannot naively implement the complex tangent method and to gauge theory with it down. So we investigate the reason why this kind of problem happened. So as I said, these two problems are trade-off. So actually, they are related. So first, we consider the transition of topological sector. So each configuration can be classified into topological sector by measuring Q log. So even if we use Q sign-like definition in the action, but we can use logarithmic definition of Q as an observable. So we can, and it's given integer value, so we can label each configuration by Q log. So the transition among different topological sectors can be seen as a change of Q log. So we plot the history of Q log. So this simulation is a complex tangent method. So, but dynamical variable is complex. So this Q is not real. So there is a small imaginary part in this case. So I only put a real part in this plot. So you can see that there is a change, discrete change of Q log. It corresponds to the transition between topological sectors. And simultaneously, we also observe the maximum drift time. So this is a plot of history of drift time. So we can see very spiky behavior. So it corresponds to this power of tail. It's a very large drift time. And there is a correlation between change of Q log and appearance of large drift terms. So I explain origin of large drift term, why this kind of correlation is observed. So transition among topological sector is caused by branch crossing of the phase of bracket, because we use a complex logarithmic function in the definition of Q log. So the discrete change of Q log is caused by branch crossing of this phase bracket. So there is a problem around the branch cut of the bracket. So we check the flow diagram of the bracket. Flow diagram, it means we'll drift term of this thing. So if we choose one of the lattice site, and let's consider this bracket, the phase is given by phi, and look at this ring. The drift term is given by the function of this bracket and also this bracket. So for simplicity, I fix the lower bracket to just 1. So now drift term is function of phi. So and phi is now complex phases. So we can plot the drift term, vector field of drift term in the complex phi plane. So this axis is the real part of phi, and this axis is the imaginary part of phi. So this vector field is gathered to the origin. This is actually effect of kinetic term. So kinetic term try to make the configuration close to unity, and bracket to unity. However, around the branch cut, so real part of phi is plus minus pi. There is a flow to imaginary direction. So this is a drift force pushing phi away from the real axis. So actually, this is a source of non-unitarity. And if we check the magnitude of drift term along this line, we get this graph. So this is a plot of magnitude of drift term as a function of imaginary part of phi. So if we go away from real axis, magnitude of drift term increase exponentially. So it means if the phase of bracket approach the branch cut, the drift force push the phase to the imaginary direction. So this flow increases the non-unitarity of the bracket, and it gives a very large drift term. So that's the reason why the topological change of configuration and appearance of large drift term is correlated. So when the topological charge of configuration changed, the large drift term tend to appear. We need to improve this point. So I will explain the modification of the model. Actually, we use introducing a puncture. So I will explain how it works. So this is a press prediction for avoiding the freezing. So by introducing a puncture on the torus, Q is no longer integer, because this is some kind of modification of boundary condition. The torus with a puncture is not no longer compact manifold. So the topological charge is not integer value. But in this case, topological charge can change frequently. It is not restricted in integer. So freezing is expected to be solved. So in terms of lattice action, we eliminate one of the bracket from the action. So if the explicit formula is like this, we don't include the one of the bracket in the kinetic term and also in the topological charge. So we call the model with puncture is a punctured model. So again, we compare the two types of definition of topological charge. So actually, this is different from the case of torus. Now it's a punctured torus. So for both definition, Q is no longer integer. But Doris term, so not only sign-like definition, but also logarithmic definition is well defined. Actually, if beta is large enough. So on the punctured torus, we can also use a logarithmic definition. Because actually the link variable around the puncture, so these green links, gets a non-zero drift terms. So we get well-defined drift term. So in the following discussion, we consider this logarithmic definition. In fact, we also perform a simulation with sign-like definition, but basically they are same. So I only pick up logarithmic definition in this talk. So let me explain the property of punctured model. So topological charge is not an integer now. So the 2 pi periodicity of theta is disappear. This is a very important point. But the functional model is equivalent to the infinite volume limit of the original model in this parameter region of theta. It can be proved by analytically. So if we write an analytic formula of partition function on the non-punctured model, I mean original model, the partition function given like this. Now I is some integral like this. On the other hand, on the punctured model, the partition function is given like this. The difference is a summation over n here. For original model, there is an infinite sum over n. However, punctured model, n is only 0. There is no infinite summation. So if we take an infinite volume limit, I mean, take v to infinity. So in this case, in fact, only n equal 0 survive in this case, if theta is between -pi to +pi, because this factor, this integral, is largest if n is close to 0. And I mean, this exponent close to 0. So we can prove that in the infinite volume limits, these two partition function approaches only in this region. We can check it by via calculating the analytic observable. So this purple line corresponds to the non-punctured average bracket on the non-punctured model. For this case, lattice size is 10 by 10. In this case, lattice size is 20 by 20. And this green line, this line corresponds to infinite volume limit of the non-punctured model. So you can see that if we increase volume, so this purple line approaches this green line. On the other hand, this orange line corresponds to the observable or punctured model. This is a volume independent. So, and you can see up to theta equal pi, the infinite volume result and the punctured model result is agree with each other. So even if we put puncture, we can get some information of infinite volume limit of the original model. So let me show the result of the punctured model analysis. So we get we check the drift term distribution. So this is almost the same as the non-punctured model. So for smaller beta, the condition of correct convergence is not satisfied. However, for larger beta, that condition is satisfied. On the other hand, if we look at the freezing, especially for large beta case, actually freezing is disappear, because you can see, you can confirm that by comparing analytic result and simulation result. This is a distribution of topological charge. So now it is, Q is not integer, so it's distributed smoothly. And simulation results almost agree with analytic prediction. So in the punctured model, both of the problems are resolved if beta is large enough. So in this case, in this green line. So long convergence and freezing problem is resolved. And let me show the result of observable. Again, we choose average bracket. For small beta case, it corresponds to this purple line. So the condition is not satisfied. So the observable deviate from analytic value at theta not equal to 0. But on the other hand, large beta, in this case, complex tangent works well. So the simulation result reproduces the analytic solution. Actually, we check the other observable. But so I skipped that. Okay, let me explain why punctured model is better than original model. So due to the because the phase of puncture changes freely, because this degree of freedom is eliminated from the action. It means that topological charge can change easily via this degree of freedom. And if beta is large enough, branch crossing of the bracket included in the action is suppressed. So only the eliminated bracket go across the branch cut. However, the bracket included action it does not go across branch cut. It means the source of large term is absent. Now, it is confirmed by checking the distribution of the phase of bracket and puncture. So I brought a histogram of phase of bracket included action and also phase distribution of phase of puncture for small beta case and large beta case. You can see that phase of puncture is almost distributed uniformly. It means phase of puncture changes freely. On the other hand, the phase of bracket included action is localized around 0. But for small beta case, there is a branch crossing happen. I mean, its approach theta equal, so this phase it approaches pi. But for large beta case, this distribution does not approach theta equal plus minus pi. So in this case, branch crossing does not happen. So in this case, the source of large term is absent. So let me summarize. So Monte Carlo simulation of the gauge theory with the theta term is difficult due to sign problem. So we tested the validity of the complex Langevin method for 2D U1 gauge theory with the theta term. But the naive implementation of complex Langevin method fails due to the wrong convergence and also topological freezing problem. That is because transition among topological sectors leads to large order term. These problems are correlated, and they are trade-off problem. So we cannot avoid both of them. So to avoid the topology freezing, we introduce a puncture. Then both of the problems are resolved, and the exact result is reproduced if theta is large. And we also prove that the punctured model is equivalent to the infinite volume limit of the original model for fundamental domain of theta. And I will explain the future work, the ongoing work. So we are now trying to apply our method to the four-dimensional SU2 gauge theory with a theta. Actually, there is an interesting prediction by Hooft anomaly matching condition. So at theta equal pi, this is a in this point phase transition happen. But in this phase, we don't know. There is a two possibility. One is a spontaneous symmetry breaking of CP symmetry happen, or it's a gapless theory like CFT. There's a two. We don't know which scenario is realized. So Hooft anomaly matching condition gives the information about each of these scenario are realized, but we don't know which scenario is realized. So we can check this scenario by direct simulation and lattice simulation. So we are now trying to do this work. So now we have some preliminary result. For small beta case, the condition of correct convergence of complex Langevin method is satisfied without the topology freezing. So this is a different point from two-dimensional U1 case. So for 2D case, the wrong convergence and topological freezing is trade-off problem. But in 4D case, we can avoid both of problem in some parameter region. So this is a very different from 2D case. On the other hand, for large beta, topology freezing occurs. This is same as 2D case. So, but it will be resolved by introducing a puncture. So we will try to introduce a puncture on 4-dimensional lattice. And we also expect that the equivalence of punctured model and the original model is also hold for 4-dimensional case as well. So even for fine lattice, we can get some information about the phase transition at theta equal pi. So this work is now a very big collaboration of 7 people. Thank you for listening.
Well, let's thank our speaker, all of us. So there's some time for some questions. Let me ask you one. I mean, freezing of configurations in a specific topological sector is a usual problem that happens with in many well-known systems, and usually people apply appropriate gauge cooling techniques. Have you considered such methods that or they are bound to fail for some reason?
You mean gauge cooling?
Not the gauge cooling that one uses in a complex Langevin. there are other gauge cooling techniques that are try to that they help the system to tunnel through different topological sectors.
Yeah. In fact, this freezing is a problem of autocorrelation. So this statement means autocorrelation length of topological charge is very long. So the autocorrelation length is increases almost exponentially if we increase beta. So if we can actually we tried some technique to handle this problem, but actually it's not good. And yeah, actually this
excuse me.
Yeah.
So sorry. Are you talking about the reweighting?
Reweighting?
I mean, Costas, are you talking about the reweighting method?
No, not
No.
Really. I mean, without any complex action. I mean, not referring to the complex action problem at all. I mean,
I see.
So, I mean, so our choice of putting a puncture is motivated by the modification of boundary condition.
Yeah. This
So
is very, yes.
It's a somehow very straightforward. Yeah. So, are there any?
It's not important. I mean, okay. Yeah. Are there any other questions? Please unmute your mic and ask any question you like. Okay, so thank you very much. Let's all thank our speaker again.
Yeah, thank you very much.
Thank you.
Okay, let me say hi to all my friends.
Hi. Ευχαριστούμε.
This is George Zufano.
Using the computer, Eleftheria. Λοιπόν, φεύγω Κώστα, γεια.
Έγινε. So Akira, the meeting is yours. You are the host, so you have to end the meeting when you like.
Yeah.
Thanks for the nice talk. This is Antonis from Athens.
Well, it's good to have another lattice person.
Unfortunately, I missed the first half of the talk, so it took me some time to catch up with the talk. So,
yeah.
Thanks for the very nice talk.
So sorry, I forget to put the archive number of this paper. So
I will find it. Don't worry. We're big kids.
Yeah.
if I may ask a question, although the question time is over, if you allow it.
Yeah, please, of course.
It's okay. Yeah.
Has there been any check of this? This puncture idea is very interesting. Have you checked that with the sigma models, like the O3 sigma models, which are also can contain a theta term on the action?
We didn't check the other model. We only studied
you
the
went
2D one.
straight to the to the U1 theory.
Yeah.
I just wonder if, because there it's an old problem how to precisely define a topological charge of the sigma model, the O3 sigma model on a lattice, on a 2D lattice, and there are various productions, various checks in the past by people. So puncture, this puncture idea is very interesting. It might work also there.
Yeah, so on two-dimensional cases, it's very straightforward.
Straightforward.
Just remove a puncture from the 2D torus. So we are now trying to generalize this idea to four-dimensional cases. So four-dimensional lattice is more complicated than this figure, and also the definition of topological charge is also more complicated. It's like so-called figure 8, like this kind of combination of two brackets, we get as topological charge for four-dimensional case. So in this case, we cannot define, we cannot simply define the topological charge which gives exactly integer number. So the definition of topological charge which gives integer number is very special property of 2 dimension. It's not for 4D. So the situation is very different.
Does the size of the puncture play any role? Can you control the finite puncture size effects?
Oh, so actually, in the analytic expression, the size of puncture is not important because you can see that this partition function depends on only the volume. This volume corresponds to the number of brackets. So the size of a puncture and the shape of a puncture is irrelevant for analytic expression. But for numerical sense, actually, it's not somehow important because I didn't think when you main slide. There's some problem for unitarity norm. So unitarity norm is some quantity which observes the non-unitarity of the configuration. So this is we define local unitarity norm on the 2D lattice. So this position is puncture. So you can say that the non-unitarity on the puncture is very high. It's 10 to the 4th. So this is a for link, and this is a absolute value of bracket on the lattice. So it observes the non-unitarity of bracket. It's also it has very sharp peak at puncture. So in numerical sense, the non-unitarity tend to be very large around the puncture. So this non-unitarity depends on the size and also shape of puncture. I think the eliminating only one bracket is minimal modification and minimal puncture. So actually, in terms of complex Langevin condition of correct convergence, even if we get very large unitarity norm, this condition is basically okay. It's not affected the effect of unitarity norm because this unitarity norm is basically stable. It's not fluctuate so much. So it's not affects the drift term. However, it is difficult to tolerate such a very huge number numerically. So there's a bit technical problem. So basically we can choose any shape, any size of puncture, but for technical reason, we choose minimal puncture in this research. Yeah, so actually in many previous work using complex arrangement method, we thought very huge non-unitarity is result in the failure of complex arrangement method. But in this case, even if non-unitarity is very large, but still convergence condition is satisfied. So this is somehow counterintuitive. I think it's interesting point, yeah, of this model.
Thank you.
So now time is 8:30 p.m. in Japan. So maybe
it's the middle of the day in Greece and quite hot.
yeah. So if there is any question, I will close this session.
Thank you very much for giving us a really nice talk.
Yeah, thank you very much.
Well, we're looking forward for more talks from you or collaborators.
Yeah, that may be interesting.
Host you.
Thank you, Kostas, for organizing this seminar.
Yeah, thank you.
Well, very nice seeing you. Have a good evening.
You too.
Okay, thank you. Bye-bye. Thanks again.
Bye-bye.
Thank you.
Bye.
Bye.